Hello, I'm Jason, a new products manager here at Renishaw. I'm responsible for managing the development of our new additive manufacturing system, provisionally referred to as EVO Project. EVO Project is our first additive manufacturing system to be fully designed and built in-house. It addresses the market requirement for a system focused on industrial production, with a strong emphasis on automation and reduced operator interaction. Last November, I flew over to Euromold with some of my team to witness the debut of EVO Project, where I met professionals from various industrial and academic backgrounds. We were really delighted with the positive feedback from all sectors, with feedback focusing around one of our key goals, designing a system for industrial production. This requires a high level of repeatability and precision between builds, something we've addressed with the inclusion of Renishaw's Resolute encoder on the Z-axis. Renishaw's Resolute encoder is a true, absolute, fine-pitch optical encoder that has an astonishing resolution of just 1 nanometer, even at speeds up to 100 meters per second. The encoder allows us to achieve sub-micron control of the Z-axis. Behind these doors, we have a high-capacity filtration system and a system responsible for the automation of powder handling and recirculation. Together, they result in the ability to run prolonged build times with minimal manual handling of metal powders. At the heart of the system, we have a high-powered 500-watt laser. Directing this power requires precision delivery. The optical system has been designed and manufactured in-house by Renishaw's leading engineers and scientists. The brain of the system is sophisticated software engineered to control the whole system. Through upgrades, the EVO Project machine will be able to include in-situ monitoring technologies that will enable detailed process analysis. This process analysis is useful in the verification of build parameters, giving our customers confidence in the parts they have produced. We're going to be publishing more information leading up to the release of the machine, so sign up on renishaw.com/EVO Project to stay informed.
By leveraging and extending HP Multijet Fusion technology for printing 3D plastics, HP Metaljet can propel your business forward with the most advanced metals 3D printing technology for mass production. Get ready to take on new jobs and unlock new revenue streams. Inside the printer, the carriage features 6 print heads arranged across 2 print bars. Up to 4 different nozzles can print HP binding agent in the same 21-micron grid on the powder bed, providing 4 times nozzle redundancy. The printing process starts by spreading a layer of metal powder. Then, HP Metaljet binding agent is jetted at precise locations onto the powder bed to define the geometry of single or multiple parts. The energy source helps evaporate liquid components and cure the material. Once printing and depowdering processes are complete, a high-strength green part is removed from the build unit and sintered using an industry-standard sintering solution. The loose powder is recovered from the HP Metaljet powder removal station and transferred to the HP Metaljet powder management station, where it is automatically mixed, sieved, and loaded into another build unit for the next job. HP Metaljet breaks through the productivity, quality, and cost constraints of existing 3D printing technologies for metals. Compared to powder bed fusion, HP Metaljet produces more isotropic grain structure in the sintered part, resulting in more uniform material properties. Compared to metal injection molding, HP Metaljet technology eliminates the time-consuming debinding process, freeing up to 20 hours from your workflow. Now you can accelerate innovative designs and products and efficiently produce high-quality 3D metal parts at scale. Get ready to experience unlimited capabilities. HP Metaljet. Reinvent.
Hi, I'm Tom from Rapidia, and today I'll talk about our new metal 3D printing system. It uses a water-based paste to print strong parts from both metal and ceramics. It's similar to existing bound metal printers, but with 3 major advantages. The first is that these machines are all you need to go from a CAD file to a strong, finished part. You don't need an additional debinder. The second advantage is that We've done away with the need for most extensive metal support and a raft or base plate under your part. And this allows you to save printing time, material, and money. The third advantage is that since the part after the printer is made of a water-soluble material, with simply a paintbrush and some water, you can bond two components together to make a more complex shape. And this also saves on material and support. Let's go through the process. The material comes in a cartridge, for example, 17-4 precipitation hardening steel. You add it to the station here, and there are spaces for 4 cartridges on the printer. It feeds to 2 print heads, which are separate and can move independently. This allows you to print 2 copies of the same part, mirror images, different parts, or alternatively, you can print a complex part with support. Once you're done printing, you simply remove the part and then move on, and then it's time for the furnace. So our furnace has quite a large volume, which allows you to sinter many components at the same time. It's also graphite free, which allows you to sinter even the most demanding metals. And finally, it plugs into a standard 240 volt outlet like you'd have in your kitchen for your stove. Let's open it up, and we'll put the part in. Now you go to the computer and you select the material, and we have a number of predefined cycles for the materials that we're able to print. You press run, and the part will be finished in the morning.